On the last video, we learned the divergence test, which is the first test that we want to run when looking for the convergence or the divergence of a series. So once again, the harmonic series, remember that 1 over k, the series of 1 over k, 1 plus 1 half plus 1 third plus 1 fourth plus 1 fifth. If we apply the divergence test to it, we take the limit of the terms. Again, we get 0, right? The limit as k is approaching infinity of 1 over k, of course, is 0. And remember, that means that we are inconclusive by the divergence test. It tells us nothing. So we need something else. We need another test. But this is a nice one to look at to consider our next test, which is called the integral test. So let's take a look at that test. On the screen, what I have projected is the graph of 1 over x. So remember, we're considering that harmonic series, the summation of 1 over k, or 1 over n. And take a look. If we consider that harmonic series where we're adding 1, 1 half, 1 third, 1 fourth, it actually connects to a Riemann sum that can be used to estimate the area under the 1 over x curve. So take a look, just remembering what we know about integrals, we're going to connect that to what we're trying to do with series here. So we've got this function 1 over x, it's graphed right here. And I have on the screen an image from the book where we have the Riemann sums under the curve, or actually it's over the curve in this case, the way we've built it, because we're using the left-hand endpoints to create those Riemann sums. We're getting 1, we're getting 1 half. The width of each of these, because we're looking at it on just those integers, so the width, or delta x, for each of these is 1. And so 1 plus 1 half plus 1 third plus 1 fourth, all the way out. When we go all the way out to n plus 1, because we're using those left-hand endpoints, that left-hand endpoint, the height of that last rectangle is going to be 1 over n, and we're going to get the sum of all of those rectangles, which is actually the series. It's the partial sum of the series up to n. That is going to be greater than the integral from 1 to n plus 1. So just connecting, if we think about, let me grab my pencil here, if we think about what the integral is this area under the curve, the exact area under that curve to the x-axis from 1 to n plus 1. That is my highlighted area, and clearly the Riemann sum that we created here, that very specific Riemann sum, is going to be bigger than that. So that Riemann sum that is giving us the partial sum, S sub n, is going to be greater than the integral. Well, we know how to calculate. This is an improper, well, it's not an improper integral yet, but we are going to let n go to infinity. This is just an integral, and we know how to compute integrals. So if we could compute the integral there, then we could figure out what's happening to the actual series. And so when we take the integral, take a look here, the partial sums, S sub n, if we're adding all of those up, that is equal to the area of the rectangles. I'll try to get the picture on the board. It's equal to the area of the rectangles, which is, as we can see visually, greater than the integral from 1 to n plus 1. But that's just a simple integral. That's just the natural log of x, and we evaluate it from 1 to n plus 1. So the natural log of n plus 1. So we end up finding here that the partial sums, S sub n, is just equal to the natural log of the absolute value of n plus 1. We don't really need the absolute value because n is a positive integer, but the natural log of the absolute value of n plus 1. But how do we determine if a series is converging or diverging? Well, we take the limit of those partial sums as n is going to infinity. So we're going to take the limit of those partial sums, because we know that those are greater than the limit of the natural log of n plus 1, and that is equal to infinity. I wrote equals up here. The partial sums are actually not equal to that natural log. They're actually greater than that natural log. And so we end up getting infinity, which of course is going to mean that our harmonic series is diverging because the partial sums are growing without bound. Now, we've looked at that in a variety of ways. We looked at that graphically. We plotted the partial sums on a previous video. We took a look at what those are doing, and we even looked at a little table where we had some estimations of the partial sums. But the harmonic series is diverging, and we can see that by comparing it to an integral of the function 1 over x. And this connection to a function, taking a series and connecting it to a function and using our integral strategies to consider convergence or divergence, is what we call the integral test. And so the integral test is this. We'll abbreviate it with IT. we're going to take a series, and it doesn't matter, we can let it start k equals n, where n is some integer, and of a series, we'll call the terms a sub k. And what we're saying here is if there is a function, f of k, so that each of the terms in the series is equal to the function's output when we evaluate it at the integers, and that function is, now there are some criteria here that are important, where that function is continuous, positive, and eventually, I did put that in parentheses, I'll underline it here, we'll talk about that as well. As long as it is continuous, positive, and eventually decreasing on the interval n to infinity, then we can consider what happens to the integral of this function, f of x. So if the integral from n to infinity of f of x converges, then so too will the series. If the integral from n to infinity of the function diverges, then so too will the series of k from n to infinity of a sub k. So if the integral is diverging, the series diverges. If the integral converges, the series converges. Now, quick note, couple little comments. Again, remember in our table of tests, we will also have some comments that we'll want to consider when we're applying the test. The integral test is only telling us about the convergence and divergence of a series. The value of this integral, if we get convergence, we will have a value for the integral. The value of that integral is not equal to the value of the series, but we have some what are called estimate theorems or remainder theorems that we can use to estimate the value of the series, but it is not equal to the value of the integral. So again, we could go back to that image that we had up here, and we can see that if this is actually a diverging series, the harmonic series, but you can see if we're using the integral, the highlighted area that I have highlighted on the graph, that would be what the area, the integral is equal to the exact area under the curve. And clearly it's not equal to the Riemann sum. It's an estimate. The Riemann sum is an estimate for it, or the area would be an estimate to the Riemann sum. They're not equal, but they can be used to determine just the basics of convergence and divergence. Okay, so one other note. The first one we've already discussed, that was in the comments of the actual test itself, and I just talked about that. But the convergence of a series is not actually affected by a finite number of terms. So basically what that's telling us is that we can move the start of the series or the start of the integral if needed. So for instance, if we have a series from k equals 1 to infinity of a sub k, those are the terms, we can actually judge the convergence or divergence of that series by moving the start of the index to, say, let's just call it some capital N, and consider the integral from capital N to infinity instead of starting at 1 to infinity, capital N to infinity of f of x, as long as a sub k is equal to f of k on the integers. This can be useful in cases where we don't meet the conditions needed for the integral test. So this can be useful in cases where it takes a few terms, and when I say few, any finite number of terms, for the function that we're considering to be continuous, positive, and decreasing. So remember on the integral test that we do have the criteria that is listed right here. Let me grab my pen. We must have a function that we're working with that is continuous, positive, and at least eventually decreasing. So we do have to meet those conditions, and we have to show that those conditions are met before we can get into looking at the integrals and making the connection back to the series. All right, so let's take a couple of series and apply the integral test to determine convergence or divergence. So here we're looking at a series from k equals 3 to infinity of 1 over k squared plus 9. And we want to use the integral test to consider whether this is converging or diverging. So if we're going to use the integral test, we first have to think about a function. So the function that we would be looking at here would be 1 over x squared plus 9. The next thing that we have to do is we have to verify that it meets the conditions. So let's verify the conditions of the integral test. So for the integral test to work, we must, one, have a function that is positive on the interval that we're looking at. Now here, k is starting at 3, so we're going to be looking at x greater than or equal to 3. So f of x is positive, and some of these are almost like visual, positive. Some of these are going to be visual or intuitive, our intuitive math sense checking of conditions, sometimes they won't be so obvious. But in this case, we can see that x squared plus 9 is always positive. This is also a continuous function. So this is also continuous. It's actually continuous on the reals, which means that it's continuous from 3 to infinity. This function does not have any discontinuities. The denominator is always positive. It's always greater than 0, so there's no infinite discontinuities. It's a nice continuous rational function. We've worked with functions of this type before, so that's clear, and we can go ahead and make that statement. Now, we also can tell that f of x is decreasing. This one might take a little bit more work or a little more thought, but this is definitely going to be decreasing on 3 to infinity as well. So why is it decreasing? Well, what we can do is we can think of what happens at x plus 1 compared to just at x. And so if we think about 1 over x plus 1 squared plus 9 and compare that to 1 over x squared plus 9, this denominator is larger than this denominator. Therefore, the reciprocal 1 over x plus 1 squared plus 9 has to be smaller than 1 over x squared plus 9, meaning that the terms as we go along are definitely, the terms of the series and the function itself is definitely decreasing. So this is a decreasing function. We'll talk about on the next example, sometimes this task can be a little bit more challenging to consider or to think about. And we have other ways to consider or to determine where a function is decreasing or increasing. Okay, so once we've verified the conditions, we've identified the function, we've verified the conditions, the next thing is to actually do the integral and see what happens. So now we're going to say, well, let's now consider the integral from 3 to infinity of 1 over x squared plus 9 dx. Well, that's an improper integral. So when we deal with improper integrals, the first thing we do is, well, it's improper, obviously, type 1. So the first thing we do is we replace that upper bound with a t, and we're going to let t go to infinity. So little refresher on improper integrals here. And the integral of 1 over x squared plus 9 dx. And all of our integration skills that we learned in the last unit are going to come in handy here because this is a inverse tangent or an arctangent form. It's x squared plus a squared here, where a is 3, so it's x squared plus 3 squared. So this is going to become the limit. As t is approaching infinity, we end up with 1/3 inverse tangent of x over 3, and we're evaluating that from 3 to t. And then we'll take the limit. I'm going to put that in brackets because we need to do that evaluation first, and then we're going to take the limit as t approaches infinity. And we'll keep moving along here. This is going to be equal to the limit as t is approaching infinity of 1/3 inverse tangent of t over 3 minus 1/3 inverse tangent of 3 over 3, which is 1. So we're looking at the inverse tangent of 1. Well, the inverse tangent of 1 is pi over 4. And the inverse tangent as t is approaching infinity. So we're thinking about, little sidebar. Hopefully we remember our inverse tangent, but our inverse tangent graph looks like this. This is the inverse tangent of x, and it has those horizontal asymptotes at pi over 2 and at negative pi over 2. So as this is approaching infinity, and we're looking at the inverse tangent of infinity, 1/3 times the inverse tangent of infinity, we know that that approaches, as we're letting t go to infinity, we know that that is approaching from our little thought bubble over here. We know that as we're approaching infinity, heading out this direction, that our inverse tangent is approaching pi over 2. So that's 1/3. I said 1/3 as I was writing it. 1/3 times pi over 2. And so we end up with, let's see, pi over 6 minus pi over 12. So let's find a common denominator there and clean that up just a smidge. and we get pi over 12. Okay, so what does that tell me? Let's get it all on the screen. What that tells me right there, that pi over 12, that's telling me that the integral that we're looking at converges. Remember, when we get an improper integral and we take the improper integral, and once we take the limit, if we get a finite value, it means the integral is converging. So we have a converging integral, which by the integral test means that the series itself. So we're not done yet. Now we say, therefore, the series 1 over k squared plus 9 from k equals 3 to infinity also converges by integral test. And I'm just going to write IT for short for integral test. But we know that the series converges by the integral test. Now, those notes that we were talking about earlier, this is not actually, not even necessarily. It could be used as an estimate, but this is not the value of the series or the sum of the series. This is not the value. It can be used as an estimate. We can talk about how close we need to get in order to get the estimate, or however close we want to be to minimize our error in the summation. But this is not the actual value of this sum. All we know right now, and all we know is what I have boxed, is that we have convergence. We don't know exactly what we're converging to, but we do have convergence for this series. Okay, let's look at another one. Okay, let's take a look at another one. The series from k equals 2 to infinity of the natural log of k over k. Same instructions. Let's use the integral test to determine if this is converging or diverging. So what is the function that we want to look at? So we want to look at the function natural log of x over x for x greater than or equal to 2. Now, when we're doing that, we need to verify the conditions of the integral test. So when we're working with a test, like the integral test, we have to start by verifying the condition. So we can see, we do know that x is obviously, if x is greater than or equal to 2, the denominator is positive. And the natural log of x, if I can just quickly give a little visual, there's the natural log, there's 1. The natural log of x is positive for all x's greater than 1. So since our x's are greater than or equal to 2, it's definitely positive. So this function right here, we could say this is sort of, I should put that into a little thought bubble. This is the thought bubble that we're using as we're verifying here. So our first two conditions are pretty easy to check. F of x is positive on the interval from 2 to infinity, check. And the other condition is also fairly easy to look at. It is also continuous on the interval from 2 to infinity. Now, there is, here, I'll put it in red. There is one spot of discontinuity for this function, but that's at 0, which is not on the interval from 2 to infinity. So, it is discontinuous. There's an infinite discontinuity at x equals 0. Yeah, just at x equals 0. I was going to say it's equal to 0 when x equals 1, but that's in the numerator. So it is discontinuous at x equals 0, but that's irrelevant to the interval that we're looking at, since we're looking from 2 to infinity. Now, this other piece is a little bit harder to just verify visually, as we've been doing. So the third part, f of x is decreasing. That's what we want to consider, is decreasing ... question mark. And I will put a question mark there. So how do we figure out where it's decreasing when it's not as easy as just the denominator, right? From one term to the next, the denominator is getting smaller and smaller and smaller, or the denominator is getting bigger and bigger and bigger, meaning the terms are getting smaller and smaller and smaller. So how do we do this if we don't have kind of an obvious inequality that we could build? So how can we consider where it's decreasing? Well, this is where we can determine where functions where f of x is decreasing using the derivative, using some Calc 1 tools. So if we want to know where a function is decreasing, all we have to do is take the derivative and figure out where the derivative is positive and negative. So what is the derivative? So we take our function, the derivative is 1 over x times x minus the derivative. I'm using quotient rule here, going through this kind of quick. 1 times the natural log of x, all divided by the denominator squared. So it turns out my derivative is just 1 minus the natural log of x over x squared. Quick review of Calc 1 content. If we want to know where that function is increasing or decreasing, we then find the critical points. And the critical points are where the denominator is 0, creating undefined for the derivative, or when the numerator is 0. So when the numerator is 0, let's see, when 1 minus the natural log of x equals 0, that's when the natural log of x equals 1, or when x equals e. So I end up with 2 critical points. And when we're thinking about our critical points, we've got 0, we've got e, which, by the way, e is approximately 2.718. And the domain of the function, we have to be greater than 0. So there are no values here. Strictly greater than 0. Let's keep the function on the board because of that natural log. So the domain is strictly greater than 0. We consider what is the sign of the derivative on each of those intervals. And checking the sign real quick there, if I plug taking my derivative, I'm going to highlight my derivative so I have it in my, can quickly identify it on my board. So there's my derivative. If I take something like 1 right now, this is going to be positive. So the function actually starts off by increasing, but then after e, if we plug in something, to the right of e and we plug this in, we can see that the function is going to be decreasing for all values greater than e. So this function f of x decreases for all values from e to infinity. Well, what does that mean? Well, that means that it's not always decreasing. This is that piece that I was talking about. It's not always decreasing. Let's come back to what we're trying to verify here. It's not always decreasing, but it does decrease from e to infinity. So it does eventually. That's what we call eventually. And it actually doesn't even take that long, only till e, which is about 2.718, and then it starts to decrease. So this function does decrease eventually, and it decreases all the way to infinity forever after e. And so it does meet these conditions because it does eventually decrease. Okay, so that said, we do have to adjust because it's not decreasing from 2 to 2.718 or from 2 to e, but it will decrease for everything from 3 on. So since we've got that considered, what we're going to do is say, thus, let's just consider the series. Let's take out that first term and let's consider the series from 3 to infinity of the natural log of k over k, and then f of x equals the natural log of x over x, and the integral from 3 to infinity of the natural log of x over x dx. And this goes back to that piece that we were talking about on some notes, that a finite number of terms in the series doesn't change the convergence or divergence. So if I consider the series from 3 to infinity instead of just from 2 to infinity, and I can get convergence or divergence, then we can go back to the series we're looking at starting at 2, and that finite, that one term that we're essentially leaving kind of floating out there for a minute, that one term is not going to affect the convergence or divergence. It would affect what it converges to, but it won't affect the overall convergence or divergence. All right, so this is an improper integral. Obviously, this upper bound is the problem. So we will take the limit as t is approaching infinity of the integral from 3 to t of the natural log of x over x dx. I'm going to do a little u sub here. U is equal to the natural log of x. So du is 1 over x dx. That makes a nice u substitution. So this just becomes the limit as t is approaching infinity of the integral from 3 to t of simply u du, which I'm going to scooch over here. This is going to be, when I integrate that, that's just going to be u squared over 2. Oh, I got to bring my limit down. Proper notation always. Limit as t goes to infinity, and we're evaluating that from 3 to t. And we still have to plug back in our u. I still haven't plugged u back in. Remember, these were x equals t and x equals 3. So then we've got, before I can do that, limit as t goes to infinity. I've got to plug in my natural log. So this is actually the natural log of x, quantity squared, over 2, evaluated from 3 to t. And then we're going to take the limit after I plug those bounds in. So let's plug in those bounds. So that's the natural log of t squared over 2 minus the natural log of 3, quantity squared, over 2. And we're going to let our t go to infinity. And as t goes to infinity, the natural log of something that's approaching infinity is infinite. Infinity squared over 2. This whole thing is approaching infinity. And we do have infinity minus, well, I mean, there's whatever this number is, doesn't really matter because we're taking it away from infinity, and this is going to be infinite. So that means that the integral that we just looked at diverges. And if the integral diverges, therefore the series itself is diverging. So once again, back to the fact that we had to bump out our start point from 2 to 3. We had to bump out that start point from 2 to 3. So the integral that we looked at was only from 3 to infinity. But when we're considering the series, if the series from 3 to infinity is diverging, then the series from 2 to infinity will also diverge. We're just adding in one more term, and that one finite term will not affect the convergence or divergence. So therefore, the series from k equals 2 to infinity of the natural log of k over k diverges by the integral test. So the series is diverging. So that one had a little more to consider because checking the conditions, sometimes checking the conditions like on our first example are going to be quick and easy. But this one had a little bit more to it when we were checking the conditions.